Throughout history, humans have developed different strategies to solve problems efficiently. Three of the most important techniques used in computer science and everyday life are divide and conquer, greedy algorithm, and dynamic programming. Each method approaches problem solving in a unique way, allowing us to break down complex challenges into manageable steps. Imagine you have a difficult problem in front of you. Instead of tackling it all at once, what if you could break it down into smaller, easier subproblems, solve each one separately, and then merge the solutions? This is the essence of the divide and conquer algorithm. 1. Divide. Split the problem into smaller subproblems. 2. Conquer. Solve each subproblem either recursively or directly. 3. Combine. Merge the subproblem solutions to solve the original problem. Imagine you need to find the word algorithm in a dictionary. A naive approach would be to flip through the pages one by one, but that would take too long. Instead, you can apply the divide and conquer technique using binary search. 1. Divide. Open the dictionary at the middle page, splitting it into two halves. 2. Conquer. Compare the middle word with algorithm. If it's a match, you're done. If algorithm comes before the middle word alphabetically, discard the right half. If algorithm comes after, discard the left half. 3. Repeat. Continue the process until the word is found or determined to be missing. This method drastically reduces the number of pages you need to check, making the search much faster. Searching for a contact in a phone book, locating a book in a library's catalog, performing efficient searches in databases. Merge sort, which recursively splits an array into halves, sorts them, and merges them back. Quick sort, which selects a pivot, partitions the array around it, and sorts recursively. And binary search, which efficiently finds elements in a sorted list. Strasson's matrix multiplication optimizes matrix multiplication by dividing it into smaller matrices. Unlike divide and conquer, which looks at the entire problem structure, the greedy algorithm works step by step, making the best possible choice at each stage. It never backtracks or reconsiders past choices, assuming that making the locally optimal decision at each step will lead to a globally optimal solution. Alright, let's break down the steps involved in a greedy algorithm. First, initialization. Start with an empty solution. Next, selection. Choose the best immediate option available. Then we have the feasibility check. Ensure the choice doesn't violate any constraints. After that, move on to solution completion. Continue selecting until the solution is complete. Finally, termination. Stop when no more choices remain. Suppose you need to make 87 pesos using the fewest coins. The available denominations are 20, 10, 5, and 1 pesos. A greedy algorithm would work as follows. First, choose the largest coin that does not exceed the remaining amount, which is 20 pesos. Then, keep selecting the largest possible coin. 4 20 peso coins, making 80 pesos total. Next, 1 5 peso coin, making 85 pesos total. Finally, 2 1 peso coins, making 87 pesos total. Since each step chooses the best option at that moment, the solution is reached efficiently. Now let's talk about some advantages of the greedy algorithm. First, it is simple and easy to implement. Second, it is fast and efficient for problems that exhibit the greedy choice property, where the local optimum leads to a global optimum. Greedy algorithms are not always optimal for every problem. They require careful analysis to ensure that a greedy approach is correct. Sometimes a problem has overlapping subproblems, meaning the same computations are performed multiple times. Instead of recalculating them, dynamic programming, or DP, solves each subproblem once and stores the results for future use. This reduces redundancy and improves efficiency. 1. Optimal substructure. A problem solution depends on solutions to smaller subproblems. 2. Overlapping subproblems. The same subproblems appear multiple times, making it inefficient to solve them repeatedly. Alright, let's dive into the steps of a dynamic programming algorithm. First, we define the problem. This means identifying subproblems and understanding their relationships. Next, we identify state variables. These are the aspects of the problem that change with each step. Then we formulate the recurrence relation. This is where we express how the solution builds from previous solutions. Moving on, we have the base case. Here we solve the simplest subproblems first. Now we come to memoization or tabulation. With memoization, also known as the top-down approach, we solve problems recursively and store the results. On the other hand, tabulation or the bottom-up approach involves solving problems iteratively using a table. When using Google Maps or a GPS system, you want to find the fastest route from one location to another while considering traffic conditions, road closures, and the shortest distance. Navigation systems use dynamic programming to compute the shortest paths efficiently. Instead of recalculating routes every time, they store and update previously computed paths. This approach ensures that real-time changes like accidents or roadblocks are accounted for without reprocessing the entire map from scratch. Network routing algorithms to find the most efficient data paths, scheduling problems like job sequencing and resource allocation, game development for AI decision-making and pathfinding. Each of these algorithm techniques, divide and conquer, greedy algorithm, and dynamic programming, has its strengths and weaknesses, and their effectiveness depends on the nature of the problem. Divide and conquer is great for problems that can be broken into independent subproblems like sorting and searching. Greedy algorithms work well when making a series of locally optimal choices leads to the best global solution, such as in coin change or Huffman coding. Dynamic programming is ideal for problems with overlapping subproblems, where storing past results avoids unnecessary recomputation, like in navigation systems and network optimization. By understanding and applying these techniques, we can solve problems more efficiently, whether we're searching for a word, planning a route, or designing cutting-edge computer algorithms. And that's a wrap on divide and conquer, greedy algorithms, and dynamic programming. Whether you're optimizing a search, making smart choices, or breaking problems into smaller parts, mastering these techniques can take your problem-solving skills to the next level. If you found this video helpful, don't forget to like and subscribe. It really helps the channel grow. Stick around and let's break the code together.